Hi, my name is Bobby Craig, and I am currently a third year statistics major here at Cal Poly. Today, I will be teaching a lesson that is following the blog of Professor Alan Rossman, which is called Ask Good Questions. Specifically, I will be looking at blog number 17, which is considering the random baby situation. So following this lesson, there will be two objectives that I want to accomplish by the end. The first will be understanding basic ideas of probability and randomness, specifically being able to determine and interpret probabilities from simple events. The second learning objective that we will be going over today is the use of simulation to estimate probability, and we will be doing this using the random babies activity, which is an applet that was created by Professor Rossman and Professor Chance here at Cal Poly. Okay, so here is the scenario. Imagine a hospital in which four mothers each just gave birth. But instead of the hospitals being able to correctly match each baby to the correct mother, they completely forget protocol. The babies all get mixed up and they end up having to deliver the babies to the mothers at random. And even though this is a complete hypothetical, it's just to get the point across. And so the question that is asked is, how many mothers end up with the correct child? And we know maybe that's zero, maybe they get lucky in all four correct matches, maybe it's in between. We don't know that yet, but we are going to look at the probabilities for this question. Okay, so the question that we are going to have overlying this entire lesson is specifically the one above. It is arranging the following events from most to least likely. Event A, no babies are correctly matched. So this means that none of the four mothers get their correct baby when it's returned to them. Event B is looking at least one baby is correctly matched to the right mother. So this could mean all the babies are correctly returned, or even just one. As long as one baby is correctly returned to the mother, that is considered event B. And then event C looks at the probability that all babies are correctly matched. So this means that all four mothers get the correct baby back from the doctors. And so the question that I want to ask is, how can we find the answer for this problem? And there's multiple ways to do it, but the biggest one that we can do that's very simple, I'm going to go over on the next slide. And so one way that we can answer that current problem, determining what is the probability that a baby is returned correctly to one mother or all of them or none of them, is we can simulate that. And so traditionally in a classroom, I would ask you to draw pieces of paper, put the number 1, 2, 3, 4 on each of them, and then pick them. And then depending on which order you pick them in and the number, that would determine what a correct match is. But because we can't do that, we can use an applet to simulate scenarios. And so what we do is we simulate, depending on how many trials we want. In this situation, we ended up doing 100, and we can see how many times one baby is matched, two babies is matched, 3 is, 4 is. And then looking right over on the right side is our frequency. So we can see that in this simulation of 100 trials, the most common response was there just being one match, followed by there being no matches, and then 2 matches, and then very unlikely to have all 4 matches, all 4 babies returned to their mothers. And one question I want to ask you guys from this graph is, why are there no trials with 3 matches? And that may seem odd because the first thought may be, oh, well, 3 trials is like 3 matches is less than 4, so why aren't there more 3 matches than 4? And the simple answer is it's impossible to have a trial with 3 matches. So this isn't just a simulation gone awry or just an outlier. It is physically impossible to have 3 matches and then 1 unmatched. And that's because if you were to have 3 correct matches, the only possible response for the 4th one would be the correct match. So that's why there's no matches or no outcomes with 3 matches. So once we look at our simulation results, we want to see if we can answer our original question. And that question can be answered by calculating the probability of each of those events, event A, event B, and event C. And we want to see if we can use probability to solve our random baby problem of which one of those events is more or less likely to occur. But before we can answer that problem, we actually have to look at what is probability and how can that be calculated. So probability is the long run proportion of times that an event would occur. And probability tells us also how likely that event is to occur. So we know that probability is scaled from 0 to 1, with 0 meaning an event will not occur, with 1 meaning that event will always occur. And somewhere in between, the closer it is to 1, the more likely it is to occur. The closer it is to 0, the less likely it is to occur. For example, with a coin flip, the probability of 1 heads is 0.5. So there's a 50% chance that a coin flip will be heads. And the way we calculate probability is by looking up the formula right over to the right. And so, for example, this is calculating the probability of event A. What you do is you count up the number of favorable outcomes to A, and then you divide that by the total number of outcomes to get that probability. So now we want to look at the question of, we need to determine the approximate probability of event B, which is the probability that at least one baby is correctly matched. So by approximate probability, that doesn't mean the exact probability, which we'll get to later. We're looking at the probability that we see from our simulation. So there's two ways to do this using our simulation data. The first is to add repetitions with at least one match. So that means it could be 1, 2, 3, or 4 matches. That all counts. So we add that up, 37 with one match, 25 with 2 matches, and then 5 with perfect matches. And then we divide that by the amount of trials we did, which is 100, and then that gives us 0.77 as the probability that at least one baby is correctly matched. And the second way to do that is we subtract repetitions with no matches. So what we do is we do 1 minus the probability of there being 0 matches, which is 33, divided by 100, and then we get 0.77 again. So we need to ask ourselves, what does this number mean? And what that means is it's referring to the probability that at least one baby is correctly matched. So that means in that simulation trial, if we ran it 100 times, we would see 77 matches of at least one. And so one of the second question that we're going to be looking at today is, how can we produce more accurate approximations for our probability? And so the number from that problem that we were just looking at refers to our simulation probability, which is different from the true long run probability. And so what can be done to make this simulation probability more accurate? And the answer to that is pretty simple: more repetitions. The more repetitions you do means that you'll have a closer approximation of a long run value. So in our previous example, we did 100 trials, but if we did say 1,000 or 5,000, we would see that our simulation probability is a lot more representative of that true long run value that we're looking for. And so when we ask the question, what do you see as number of trials increase? The simple answer is we see more accurate simulation probabilities that more closely represent the true long. There are 24 different possible outcomes here. And so continuing on trying to find the exact probability, once we know the sample space, how many possible outcomes there are, we can go through and categorize each trial by how many matches there are. And so what you would do is you would go to the first trial, so the one where it's 1, 2, 3, 4, and say, okay, how many matches are here? And you would say there's 4. And then you go to the next one and see how many matches there are, say it's 2, and on and on and on until you've done that for all 24. And once you've done that, you can determine the exact number for each match by counting up how many matches there are for that specific instance. So how many times there's one match in a pairing, how many times there's 2 matches, 4 matches, etc., and then dividing that number by the total number. And this will get you the exact probability for there being 0 matches, 1 match, 2 match, or 4 matches. Because remember, you can't have 3 matches in this problem. And so once you do that, you should come with this, with the first section, the first table being our original sample space, and then determining how many matches there are. So, like in the first row, 4 matches in that first row, first column. Second, 2 matches in that first row, second column, 2, and so on and so forth. And then we added all those up, say for 4, there is only one possible scenario out of 24 where they're all perfectly matched, and that's when it goes 1, 2, 3, 4. So you take that and then divide that for the number of trials, which is 24, and that gets you the exact probability of there being 4 matches when there's 4 mothers and 4 babies and it's randomly paired. And so that tells us the exact probability is 1 out of 24. And so we can do that for all of those, and we see that below. The exact probability for 0 matches, 1 match, 2 match, 3 match, and 4 match. And as you can see, there is no scenario where you can have 3 matches. So what we could do is compare these to our original simulation probability where we ran 100 trials, and we can ask ourselves if that analysis was a reasonable approximation of these exact probabilities. And so when we look at these side by side, we can actually see that, yes, that simulation was a pretty accurate tool in gauging that exact probability. It isn't exact. For the simulation, it's 0.33 for 0, 0.37 for 1, and it's flipped for the exact probability. But you can tell that they're relatively accurate, even though it isn't 100%. But it is a pretty strong indicator of how many matches there are. So going back to computing probability, we're going to look at our original problem, which is looking at the probability of at least 1 correct match, in addition to trying to find the probability of at least 2 correct matches. But instead of using our simulation probabilities, we are going to use our exact probabilities. So we're finding the exact probability of at least 1 match and at least 2 matches. And so I want to ask the question of how can we use a probability table to answer this? So I would traditionally take a second, and then we could see here that we could use the probability table to see how many times there was at least 1 match and at least 2 matches and add those up. And so here you could see the probability of at least 1 match. We could do our method of doing 1 minus probability of 0 matches, which ends up equaling 1 minus 9 divided by 24, which equals 0.625. And then we could do the same thing with the probability of at least 2 matches, which is the probability of 2 plus probability of 3 plus probability of 4, which is 6 divided by 24 plus 0 for 3 because you can't have 3 matches, plus the probability of having perfect pairings, which is 1 divided by 24, and that equals about 30%. And so we need to ask ourselves, what do these two numbers mean and how do they relate to each other? So for the first number, that tells us there's about a 62% chance that there's at least 1 match in the hospital, so at least 1 pairing. And then for the 0.29 number, that tells us there's approximately a 30% chance that there's at least 2 matches. And how do these relate to each other? Well, you could see that the probability of at least 1 match is a lot higher than the probability of at least 2 matches. And that makes sense because the probability of at least 1 match is pretty much at least 2 matches, but you're adding that possibility of 1. So you're adding 33%. So it makes sense that that is a lot higher. Okay. Lastly, we are going to use exact probability in what we've learned today to go back to solving our big question, ranking events A, event B, and event C from most likely to happen to least likely to happen. And so what we can do is look at the probability of these events and find it by how many times this event occurred. And so the probability of event A ends up being 0.375. The probability of event B ends up being 15 divided by 24, which is 0.625, which was actually the answer from our earlier part where at least 1 match occurs. And then the probability of event C, the probability of there being 4 matches out of the 4 mothers and 4 babies is about 4%. And so continuing on that, now that we know the probabilities of our 3 events, can we now list event A, event B, and event C in the correct order from most likely and least likely to happen? And so there we have listed again what event B, A, and C mean and their corresponding probabilities. And so a big hint here that I can give for you all is think about how probability connects to our question and how probability connects to most likely and least likely and the likeliness of something happening. Okay, so I will go to the next slide. And the answer should be yes. Remember earlier, we talked about how probability relates to how something is more likely or least likely because the closer that number is to 1 or the higher it is, the more likely it is to occur. And the lower that number is, the less likely it is to occur. And because we now know that probability tells us how likely something is to occur, we can rank our events from highest probability to lowest probability. And so the answer for that is below. We would have event B being the most likely because it is the highest, event A being the second most likely